On behalf of the Soil Information Community of Practice, I'm delighted to welcome you to today's showcase event on modeling and mapping. Thank you for joining us from around the world at this exciting session taking place today. Today, we are bringing together experts who are shaping the future of soil science, precision agriculture, and digital tools for sustainable land management. We have three fascinating presentations lined up. The first presentations would be presented to us by Betony Colman and Diana Collazos from ISRIC, World Soil Information in the Netherlands. They will introduce us to the Seedling digital soil mapping workflow, a powerful step towards better soil data and decision making. Our second presentation would be delivered by Dr. Abdel-Aziz Belal from Egypt National Authority for Remote Sensing and Space Science. He will share insight on how precision agriculture technologies can help mitigate climate change. Finally, and our last presentation will be presented to us by Dr. Maryam Lawal from Bayero University, Kano in Nigeria. She will discuss machine learning models for predicting crop yield and managing nutrients, showcasing how data science is transforming agriculture. This is an excellent opportunity to explore innovative approaches, exchange ideas, and spark collaborations that make a tangible impact on food security, climate resilience, and sustainable farming practices. So let's settle in, stay curious, and get ready for a session filled with knowledge and inspiration. Without further ado, let's begin with our first presentation. Each presentation has between 15 to 20 minutes for both presentation and questions. So I would invite Betony and Diana to take us through the first presentation. Please share your screen and you have the floor. Thank you very much, Diana and Betony.
Thanks, Eric.
Thank you, Eric.
Share the screen. Diana, maybe you should share the screen because it did not like that. Sorry.
Okay. Give me a second. I find the. Okay.
While she's finding that, just to introduce us, me and Diana are colleagues at ISRIC. We're both GIS technicians. We do a lot of the mapping work for various projects within ISRIC. Today we're presenting the Seedling, which is a digital soil mapping workflow. It was mostly developed by our former colleague Julio, but now we're taking on the role to continue developing it and continue going with it. So that's what we will present to you today. Now I hand over to Diana.
Okay, just make sure, can you see the slides?
Yes, Diana.
Yes, you can see it. Yeah. Okay, so the presentation title is Introduction to the Seedling Digital Soil Mapping Workflow. First, we're going to do a short presentation, then a short demonstration on how to set up and run the workflow, and then some questions and answers. So the digital soil mapping workflow, like in general, not only ours, but in general, will share these common features. You put some inputs, which usually are soil measurements, so points and coordinates. So this is what we mean by observations. And covariates, which are rasters that represent environmental features that can influence the modification or formation of soil. Then you clean that data, harmonize it, and do a extract, so the value of the covariates on the points, then that's called a regression matrix that goes inside a model that is fitted. And you can also do some improvements to the models, like select the covariates that are more related to your data. You can find the parameters that work better for the data, and also do some internal assessment. And then with that, you run the model and create some predictions. And at the end, you usually want to assess how good is your model to see if these maps that you got makes sense. So it's usually these very common features, and they share names, these digital soil mapping workflows, and it's usually modular, meaning that there are different steps that are like connected in a workflow. And the particularities about the Seedling workflow developed by ISRIC is that it's completely R-based, it's easy to use for people with limited experience in digital soil mapping, it's multi-platform, you can run either in Windows or Linux. Mac, it still needs a bit of testing, but maybe it's possible. And then you can run it in your own laptop or workstation. And as I was telling you, it's modular, so it means that there are different packages of functions that do different things through the workflow. It's an operational tool. It's based on the soil grids workflow. So first, ISRIC developed soil grids, and then the team thought that it would be nice to have a tool that is scalable and also easier to implement. It starts with standardized inputs, as I already explained. You prepare your points and prepare your covariates, and it produces maps, accuracy stats, plots, and more that we will show later. And what it's not a data preparation tool. You need to prepare your data before you put into your model, and it's not a training tool in the sense that you cannot learn digital soil mapping with it. You need to learn the basics first, and then here you're gonna apply that knowledge that you have. What it does, it can do 2D and 3D modeling. 2D is that you set a specific depth, while in the 3D is the depth is used as a covariate to predict, and that in the 2D it's a weighted average layer is calculated. You can also use recursive feature elimination to select the covariates that better influence your model. You can tune your parameters and do cross-validation, and usually it is implemented inside the Seedlings parallelization, meaning that your area will be divided in small tiles that will run at the same time to improve the performance of the model. And the license is open for the public. Anyone can use it. And we released the last version, the 0.4.2, and just a disclaimer that ISRIC is not obligated to provide support or fix any bugs. However, we really appreciate that if you at some point use it, you can give us some feedback. That would be really nice for us. So now I give the floor to Betony.
Thank you. Diana, I'll try to share my screen again, but otherwise.
Okay. Or
well, just for showing the next bit, it might be easier.
Okay, I will stop sharing then.
Yeah. Okay, I hope everybody can see this now.
We are seeing the
document. Sure. Okay, Diana, maybe it's better if you do it. Sorry. Brief interruption.
Can you see it now?
Yes.
Okay, continue.
So we'll quickly go through the documentation. There is documentation on Shiny app, and also there's a Git repo. we could go quickly. Do you have it open, Diana, the documentation? I can send the link if not. Here we go. So there's some quite detailed documentation. I will also share a link in the chat if anybody wants to look simultaneously. And it goes through the installation of the Seedling. It's as an R package. There's various ways to install that, either from the Git repo or it is a package itself. And then it goes through which are the required inputs. These are, of course, standardized inputs. What is needed from each of the files. Jenna, if you scroll up a second, just to go through the layers and the profiles. So you can see there, that table is an example of the profiles. In the profiles sheet, you just need the profile ID and the X and Y. In the profile ID, you should link to the layers, which should then have layer ID if that's relevant. And there you would have the depths and the various soil properties. A key thing here is that you can have various soil properties with the layers, but the Seedling at one time is only going to model one property. So you just specify in the config file, which we'll show in a second, which property you want to be modeling, but you don't need separate layers files for each property. Yeah, so for example here, this is an example of the config file, and that's where you would specify at the VOA the singular profile. The only exception to that is if you're modeling the texture. There you would obviously need sand, silt, and clay. So I think Jenna's, yeah. So for example here, you enter in the config file the names of the column which represent sand, silt, and clay in the layers file. And then just to show here, you would enter the location of the profiles, the location of the layers, the location of the covariates. That's at the top of the page. And the mask file. An important thing about the mask is that it should have an A where you don't want the model to predict. Another thing is that if in any location of the covariates there's NA, then for the prediction, the model obviously can't predict there. So that will also influence the area predicted by the model. If we go back to the presentation. Sorry. Yeah, so as said, you'll need two files, the configuration file and the workflow script, which runs the steps of the workflow. I think on the next slide there's an example of this. This is an example of the configuration file, and the most important parameters of the configuration file. Also important, of course, is the coordinate reference system of the profiles. The Seedling does reproject things if needed, but obviously you need to specify the right coordinates reference of the profiles initially, and then the output, everything is going to be the same as the mask. That's an important thing to note. Then I think we can go to the next. Then this is the workflow script. On the documentation is the complete example of that, but for here this is fine. So first it loads the R package, And then everything defined in the config file is taken and loaded. So the this workflow script, as it's called, you don't need to edit anything, simply edit everything in the config file and then just run this either all at once in the terminal, or you can run it line by line. Either is fine. Running line by line is maybe easier if you need to do debugging at some point. There are various options for optimizing the Seedling, so you can speed it up by increasing the number of cores. And there's also an option in the configuration file, which is overwrite. You can set this to true or false. If you obviously set it to true, it will overwrite everything that's set. If it's in the output folder already, it will overwrite it. If it's set to false, anything that's already run in the output folder is not going to be run again. So this is useful, for example, if you come into an issue somewhere, maybe with the model fits or something, you already have done the RFE, for example, beforehand, so you don't need to do that again. You can simply delete the outputs of where it went wrong, see if you can fix it, and then run again with overwrite equals false. However, most of the time, if you're not doing too big of an area, it's probably easiest and safest just to do overwrite equals true every time. And then also there's ways to reduce the RAM usage if necessary. So there's various options for the cores. You can, in the configuration file, decrease the number. And then there's also the option for tile size. This reduces, as Diana says, the size of the tiles that it creates, basically. Each iteration, so then it reduces the amount of RAM at one go. And here is a nice, with a tile size of 200, the prediction step uses approximately 2.2 gig of RAM per core. So it is quite intensive depending on the size that you're going for. And then we can just show what the outputs actually might look like. So this is the 3D run is the name of the output folder. So this file path is what would have been set in the configuration file, and then the maps, model, other plots and points folders are all created by the Seedling. So for example, if you open the model, so this is a version that's run PH, then you get various different metrics. Interesting ones are the RFE, 3D note. So this is the list of the covariates that have been picked up if you have chosen the recursive feature elimination option. There's then also the regression matrix. The regression matrix is also very important one, and maybe one that where you might want to use the overwrite equals false option, because presumably the regression matrix is always going to be the same.
Yeah, I'm not gonna open this regression matrix.
No,
it's huge, and so it will. Yeah.
And then the final really important one is the CV metrics, and this is the cross-validation metrics of the model. So here you have RMSE, mean error, R-squared, correlation coefficient, mean error coefficient, and the mean error. So various metrics there to see how your model's done. Key point in DSM, I'm sure you probably are aware anyway, but be wary of anything too high. So an R-squared of 0.8, for example, you might actually, while it sounds good, you might actually be wanting to look at what's gone wrong and how it is so good. And maybe there's a case of overfitting. And then maybe lastly, how quickly is QGIS going to open, Diana? Maybe we can show the map.
But it also shows you.
Oh, yeah. Plots.
It also produces a plot. So this is some test that we were doing in West Africa. So in the end, it will give you a map like this. Like this is a PNG map that the Seedling generates automatically, but you also get the geotip that you can open with QGIS and maybe use it for other models or just check pixel by pixel.
Yeah.
Yeah.
Or further analysis.
Or further analysis, yes. So I think that's it from our side. Thanks for listening. Any questions?
Thank you, Diana and Betony, for taking us through this process. And for soil mappers, I think this is a very interesting tool for us to use. And it's open access. We can use it and adapt it in our area of research and interest. Please, we have, we may take one or two questions, then we can move on to the next presentation, if there is any. Do I see any hand up? Or if you have your microphone open, please, you can go ahead with your question.
Can I ask?
Okay, Musefa, please, you have the floor.
Thanks so much. Nice to see you, Betony and Diana.
Hi, Musefa.
It's very nice presentation. I just also communicated with Chro to present my work next time in our next show event, just to show how because I used the Seedling workflow, so I will show definitely the maps that I produced for Central Ethiopia using this workflow. But one question that I have that I encountered when I used the Seedling workflow is the CV matrix, the output from the workflow is one of the output is the CV matrix. And in that CV matrix, there are only like accuracy metrics related, like model efficiency coefficient, and so on. But there is no like uncertainty related accuracy matrices, like, for example, prediction interval widths, because from the Seedling workflow, we can have like the outputs like mean prediction and also prediction interval widths by using the 95 and 5%, I mean 0.05 and 0.95 predictions. So from that, we can calculate the prediction interval widths. So the uncertainty. So it will be better to include prediction interval widths and prediction interval coverage probability accuracy metrics in that CV matrix. Maybe if there is a room, maybe further we can work in the future to include. But I'm happy that the ISRIC is making this workflow is free and open to especially for the young scientists, and also it's possible to produce like national maps and also local maps by using just this simple workflow that's produced by ISRIC. Thanks so much.
Thanks, Musefa. Also, just to comment on that, where we showed the mean, there you can also see the lower and upper quantiles. So I get your point. It doesn't say it explicitly now, but it is with the Seedling outputs possible to calculate it yourself at the moment. I think the reason it's not included is just maybe because it's an extra step of computation that would, if it is a big area, obviously take some time. But we could see if we can make it an option to do like, true or false, whether you want it to include it or not, something like that.
Nice.
Thank you.
Thank you, Musefa, and thank you, Betony. Musefa adopted the workflow and also have produced a nice research work that have been published in Geoderma Regional. So Musefa, you can share the link to your publication in the chat for participants to also have access to. I would invite...
Thank you, Eric. If you allow me 1 minute,
Okay,
also, I really, truly would like to thank Diana and Betony for introducing this important tool that we have at ISRIC to our CoP member. I'm sure it will be really useful for most of them. And thanks, Musifa, also for reaching out in the chat earlier to also your willingness to share with us your research. I may ask you, Musifa, if it is possible, like we do one session, not only as showcasing your research and publication, but also if you can take the participant through the workflow, like a few steps for like short time, like 1 hour, 1.5 hour, will be very useful because we have a lot of new scientists here and they are very new for such technique, and probably it's nice to do kind of like a demonstration session beside the showcase of your research. We can chat a bit later, me and you, and see what is possible. Thank you very much. Thanks, Eric.
Okay.
Thank you, Crow, and thank you, Betony and Diana, for such an interesting presentation. Thank you. I would invite our second speaker, Dr. Abdel-Aziz Belal, to take us through his presentation. His presentation is titled Role of Precision Agriculture Technologies to Mitigate Climate Change.
Okay. Thank you, sir.
You can share your screen. Yeah, you're welcome.
Thank you. You see my screens, Eric?
Yes.
Okay.
You can see your screen, but not in presentation mode at the moment.
This okay?
Maybe you can put in presentation mode.
Okay.
Yeah.
You see now?
Yes, we see it, but we also see the outline on the left corner. So if you can make it big, then...
Professor, yeah, if you go to that icon next to the minus sign, just at the very bottom of your screen.
The right side, yeah.
Just next to the minus. Do you see it?
No.
No, don't press the... Yeah, that one. Can you press the first one? Yes, please.
That's okay?
No, we still don't see it on presentation mode. We just see that you zoom in and out, but if you press the icon with like a monitor, have a standing there, if you press that one. Yes, that one. Can you press that one? Maybe it's not functioning.
Or maybe you could try to press F5 on your keyboard. F5.
F5?
Yeah.
That's okay?
No, still not. Maybe we can go like this. It's fine. It's fine, Professor. Don't worry. We can go like this.
Okay. Now I speak about the technology about the role of precision agriculture to mitigate climate change, and I will present how can implement precision agriculture in Egypt to mitigate and to increase the efficiency of the inputs to the crops. What is the problems? Okay, now if you see this slides speak about how can artificial intelligence come to achieve the environmental development, sustainable development goals, can use every goals for agriculture, water, and life.
Professor Aziz?
Yeah.
Please, we can't see the second slide. Please, can you click on slide show on top of your menu bar? Slide show.
Just a moment.
The slideshow on top of the home, insert, design, transition. You see the slideshow.
Slideshow. Just come see.
No, we can't see your cursor. If we can see your cursor, then where we have the file, home, insert, design, transition, you can see the slideshow.
Stop sharing. Sharing the screens. So. Okay. Sustainable development goals. If also we work in Egypt about the digital transformations in agriculture, the government make target to the digital transformation for agriculture. We use artificial intelligence, IoT, remote sensing to provide data driving insight to optimize the resource use to improve crop yield and minimize environmental impact. This approach promotes precision agriculture like smart irrigations and efficient supply chain to reduce the water and chemical consumptions, release food waste. If we see the difference between the comparison between the traditional farming and the precision agriculture, but traditional farming mostly manual work and use the machines. For precision agriculture, use machines, robotics, farming techniques. Little to no technology about the technology for traditional or conventional farming, little to no technology. For precision agriculture, use GPS or the GPS or drones, artificial intelligence, IoT, and so on. Water and fertilizers use often wasted. Why is often wasted? Due to the farmer use the farm as a unit, as the same unit, as a homogeneity units, and put all the part of the farm as the same for fertilizers. But in the precision agriculture, optimized for efficiency, but based on the variability of nitrogen, for example, or potassium or phosphorus, and the soil, for example, or crop nurturing. Some in conventional use the A, but in precision agriculture, use the real-time remote sensing drones data to crop nurturings, and they can cost cheaper to start, but high initial cost, but they save money longer times. If this is for precision agriculture, if we start, this is for building the system for precision agriculture or smart agriculture. This is cost, but after that, for the long time is saved time. Environmental impact can harm the soil and water. That is, can use much more water, also can increase the emissions of nitrogen oxides, also the methane gases. More eco-friendly, that's for precision agriculture. Also, we see this for presentation. Crop yield good, but inconstant. Higher, more variables. Flexibility, hard to adjust, adapt quality with data insights. If we make a correlation between the industry, agriculture evaluation or agriculture industry, this slide show how is agriculture 1.0 until agriculture 5.0, how to can use renewable for agriculture for 5.0 now. The people can use artificial intelligence and the net of thinking, use renewable new energy, solar energy or wind powers, can use what in traditional can use for 1.0 agriculture can use the humans or can use the human and animal powers, but now we can use the machines and smart agricultures, use AI and Internet of Things. This is how to can use the data between. This is if we have the data from satellites, from sensors, from the historical data for farmers. These data make a preparations or the analysis, make a data controlling, data cleaning, data standardizations. After that, make data development, data processing, prediction, for data processing, make the decisions. This is the decision. This is system monitoring, royal management, and the model metadata management. How does surface to come to the farmers based on for mobile applications or MSS or for clouds, can for agricultural research for farmer service providers. For Internet of Things, this is the Internet of Things can use in different management practice in precision agriculture. If we need to implement smart agriculture or precision agriculture, use IoT, can use in real times or the wireless sensors, how to can send the data and to collect the data on the cloud. This is very important. And now the people launch, and the following country launch satellite for IoT to collect the data from the farm. For Africa sometimes, or for Egypt in the desert, or the internet, we have a problem in the internet. And if we need to implement smart agriculture in the project or the developed area or reclamation agricultural land in the desert, as a smart agriculture management, you need to use IoT. I think this is a problem is solved. Can no communication satellite. Now we have low Earth observation satellite for Internet of Things, and you can collect the data and you can be able to implement IoT. What is the meaning of a smart agriculture? Smart agriculture optimize agriculture both by targeting spatial and temporal on the field within the field. Smart irrigation management or smart agriculture, especially we speak about smart agriculture irrigations, means that the right input at the right time in the right amount in the right places in the right manner. This is the definitions from Raj in USA. What is the benefit technology of smart irrigation or a smart increase the yield productions and the farm, reduce water use from 25 to 35%, reduce environmental pollution through the agrochemical, increase in special information from the target management. Precision agriculture technology that has the optional to mitigate the greenhouse gases emissions. We have three gases emissions from the sector of agriculture: nitrous oxides and methane and CO2. This is the three can make a problems for precision or for climate change, for the emission from the agricultural sectors. Now this is the rice can much more methane emissions. Also for livestock farming, have much more livestock has much more methane emissions in livestock. This is in we will show you how to can make a experiment on Egypt and develop the systems based on IoT and artificial intelligence to reduce the methane emission from the rice. This is, if we see now, this is if we go for smart sprinkler irrigation systems. This is for smart irrigations. This is, as we know, smart, not the field is the same units. We have different soil moisture also in the soils. This is the rate of irrigations, and you can put the sensors in the nozzles for spraying. You can put the sensor on the spray, how to make a controls. This is the sensors, and you can the rate for irrigation from half to zero, or this is also zero. Water can make a control. Not just see the field is the same and both the water is the same and they make a problems. This is just, we have a project in Egypt for one sprinkler, one pivot or for sprinkler irrigations. This is a pivot, this is a black one, have different soil types, have variation in soil type from sand to shell. And the shell, this is a clay soils, keep for the water for much times, and they can irrigate it every 2 days. And that make this, the black one is waterlogged, becomes a waterlogged area and the loss of yield. This is the benefit. We have a project from the scientific ministry to work in this area and develop the prescriptions maps. If we see this one, we need to make prescriptions maps. This is the prescription or variable rate maps from 0, 1, 2, 3, 4, 5. 5 is you should put much more water. 0, we don't need to put water. This is, you can collect the data from remote sensing, from 18 node calculation, from the satellite data and climatic data to produce the prescriptions or variable rate applications maps for irrigations. We have developed systems for smart irrigations for soil monitoring characteristics, and this is the soil moisture TDR sensors for soil moisture for irrigation for more different crops in Egypt. And also we have temperature sensors, ECE sensors, and pH sensors. And this is a system that sends the data to the cloud, and also we have mobile applications. Data from come to the mobile applications, and the farmer can use very easy. This is the systems, and also can work with solar energy. That's our electricity. If is available, we have two for power, energy power. We have two, one for solar energy and the other one for electricity, and submitted for patent and the Ministry for Research for patent. This is a system number one. System number two, also we have a project from the Ministry of Science of Research in Egypt, and for rice, we have Egypt planted rice, and the African countries have planting rice, and the rice take much water, and we need to reduce the water for rice from 30 to 40%. We use a smart alternative wetting and dry in high yield. How to can use these methods? We have this is the tube. For the road zones, we have classified this one. This is area to from the surface. This is the normal wetting regimes. This is the wet dry regimes, and we can classify Z20 to from the surface from 20 to 15, 15 to 10, 10 to 5, and you see make ultrasonic sensors. The system including ultrasonic sensors in the tube, put it in here in the tube, and make also calculate the water productivity to when we go the level of water, and make experimental applications to collect the water. This is the system and mobile applications. The benefit of this system is to reduce also save the water, and Egypt have scarcity of the water, and otherwise say emissions of methane gases is low, around 50% can reduce the methane emissions and can mitigate the climate change. This is a method, and also the increase the yield productions makes the test. This is for lysimeters. We use this for lysimeter for two types in rice, one for 300 super 300s and 108 in Rice Research Institute in Governorate, Kafr Sheikh Governorate in North Egypt. And we have two replications, one without, and this is 1 and 2 for the same rice type. This is for 300, super 300, and this one 0, 180. What other one, but hydrogel. This hydrogel can save the water. And also, this is the systems, also implement the systems and the experiment and collect the data. This is the teamwork and how to collect the data. And this is a valve, open water is automatically and can calculate the water, how to calculate water inputted by meters. Also make remote sensing measurement for chlorophyll content, for thermal camera, for stress, for leaf area index, and F bar, photoactive radiations, and this is a spectrodiometer to make a correlations with a barometer of the replication of and quantity of water and yield production of the rice. After we do we do that experiment for 2 years in lysometers, and after that do this an open field. After 2 years, after we see the system is okay, no problems, or can you use it, put it in the open field, and can just install the systems and make a replication also for 2 types of the rice. This is the system in the end. We have this system in the end on the open field, and this can follow meters. You can calculate the water, how to put it in the open field to make water productivity correlation with the yield. This is the main idea, to save the water and also increase the yield, and also reduce the methane emissions. Also, we have this harvesting the rice and make a calculated parameter, agronomic parameter for the yield, quality based on the different things. This is the cloud system. This is the data can come to clouds, and also comes a mobile application, and how to can open and close automatically the water through the rice irrigations. And this is the system can reduce the water around 30%. This is a diagram in the future, how to, after we finish, how to can in the future implement it in North Nile Delta in Egypt. This is the area cultivated by rice. This is the diagrams, can put the sensor when soil is homogeneity, and put it sensors in the valve, and we use the meteorological data to, and how to can use water, make a control in the farm. This is when we have the levels, level 10, we have level 10 below the surface. This is a better one, can put the water. Conclusions, we use the smart technology in agriculture management project is to adapt to climate change is very important. Reduce water use for rice irrigations by based on wireless sensors, AI, IoT, ICT, remote sensing, mobile application, and GIS. Establish special information database for agriculture management resources to assist farmer and the decision maker in implementing development plans in the country. Generalization the use of automated system in agriculture's operation to ensure the continuous production in time and for crises and disasters. And in the end, thank you for listening. And if we have any questions, I am waiting for if you have any questions. Thanks, Eric.
Thank you, Professor Aziz, for this interesting work. Yeah, it is very timely how we can see the role of precision agriculture in this climate change era that we find ourselves in.
Yeah.
Climate change is real, and we are very happy to see some of the technologies that we can adopt in our agriculture setting. I would invite questions and comment for Professor Aziz. Professor Aziz, we would also like to, if you can, open your camera so that our participant can also see you.
Sorry, Eric, we don't have camera.
Okay,
I can open my mobile. Just I can go to the mobile and I can open the camera from the mobile. Please give me just minutes and I can open. Okay, no problems.
Okay. Dear participant, please, you have the floor. 1 or 2 questions for Professor Aziz, then we would move on to our last and final presentation for today. Please, you can open your microphone and ask your question, if any. If there is none at the moment,
shall I?
Yes, please, Musefa, you have the microphone.
Okay. Thank you. I would like to appreciate Professor Abdel-Aziz for the nice presentation. And it's also a wonderful experiment to demonstrate that the role of precision agriculture in mitigating climate change. But I have one maybe question.
Okay.
I think you just demonstrated that the sprinkler irrigation application, if it is timely and with controlling the time and the amount of water applying on the rice field, is really helpful for resource utilization. It saves water, but I'm not sure if it is really helping the methane emission from the rice field. Is that because of applying low amount of water, or is that because of like controlling the time of application that really helps to decrease the methane emission from the rice field, and also then at the end helps for the climate change?
Okay, can I answer?
Yes, Professor Aziz.
Thank you, Mustafa or Mustafa. Thank you so much for your question. It's very important. But we measure the methane emissions in chambers. We have chambers to measure the methane emissions. We have some waiting and drying.
Recording in progress.
Just open the camera. Okay. Okay, yes. Okay. And
hello?
If you know the rice fields,
right? Aziz, please, yeah, can you turn one of your microphones off? Yeah, I think it would be better now, yeah.
And if you know the rice fields for the, okay? For the rice field, you hear me?
Yes, we can hear you, Prof.
Okay, can I close out?
Okay.
Okay.
Sorry. And they make each field have a valve, and from this valve, put the sensors. We have the clay soils, but most of the soil can 100 acres or the 200 acre can is homogeneity of the water. When we levels, we have ultrasonic sensor. When the level underground water is come to 5 centimeter or the 10 centimeter below the surface, this is who can make irrigations. This is, I think, this can reduce the emissions. But now, for the normal or for conventionals, the people can use the water each 2 days or 3 days, but with this system we can use each week. We can make irrigations for the rice, and I think this can reduce the gas emission from the rice fields. And we can this systems, I think we have diagrams can show you. I think for this is the diagrams how the cases. This is one can put the sensors here for rice sensors. This is the system in irrigations in Egypt now. This is we have tubes, and this is a supply valve, and this can make a automatically controls. And this is one for solar energy. Can use it, and you just can make fully controlled, and you can make water management for the rice and reduce the water. This is what tested in the field. This one just come in the full field and make fully automated and reduce, and can make chambers to calculate the gas emissions from the field rice. Okay. Any other question, Prof. Mustafa? Hello?
No more question. Just I understand. Yeah.
Okay.
Thank you, Mustafa, and thank you, Professor Aziz, for the reaction to Mustafa's questions. We would now move to our final presentation, which would be presented to us by Dr. Maryam Lawal from Bayero University. She will be speaking on machine learning models for recommendations and predictions of crop yields and nutrient management. Please, Dr. Maryam, you have the floor, and you can share your screen. Thank you very much. Professor Aziz, please, your mic. Thank you. Dr. Maryam, please, you are muted. We cannot hear you.
Artificial intelligence in other sectors. It has proven to be very effective and efficient. And for machine learning algorithm, which is a subset of artificial intelligence, it focuses majorly on development of this algorithm using data sets, and mostly known for its recommendation and prediction system. In the field of agriculture, adopting this technology will help to look at relationships between our variables, soil variable, climate, management, and the rest, that actually impacts productivity and yield. So this will help to improve the accuracy and allow the integration of these multiple data sets to develop a site-specific requirement for each study area, and then be able to predict the key outcomes based on the input features. And why this matters, especially in sub-Saharan Africa, is the fact that, number one, the soil and the microclimate varies over a short distances. That is, there is variation in the soil and weather variables. So the need for site-specific recommendation rather than the blanket application that is generally used and mostly common. And this blanket application, as we all know, is inefficient because it results in loss of resources, environmental degradation, then the carbon footprint and the rest. We all know the impact of this in our environments. So looking at machine learning algorithm, it helps to capture these relationships between variables that affect yield, soil factors, and the rest, and be able to detect the particular solution required for each of these areas, or the soil factor and the rest. This will help to improve the nutrient use efficiency and optimize yield. So by targeting our inputs, it will pay off the most. And although majority, or let me say, we have decision support tools that has actually been adopted by us, they have also proven to be quick, efficient, and effective. However, majority of these decision support tools do not put into consideration other factors affecting the soil or the yield. Like I say, factors like the weather variables, they look at the management factors and some other factors that actually affect yield. So, and another thing is that, for instance, the expert recommendation can be subjective and variable. And most of these decision support tools cannot also work with large amounts of data sets to be able to make predictions and recommendations. So looking at this, we can be able to integrate these decision support tools with machine learning algorithm to have a more or better accuracy and better results. And this will help to maintain sustainability and then curtail the challenges associated with crop production. So one of the significance of machine learning algorithm is that it can be easily accessible to farmers, policymakers, researchers, in order to make informed decisions. For instance, machine learning algorithm will help us to detect areas that actually require priority intervention and those that require balanced optimization. So the goal is to deploy it as a simple advisory tool that will be easily accessible to farmers and extension agents, researchers, and the likes. Unlike other rule-based models, the machine will actually learn from the data set, from the region-based data sets, whatever data sets that's being used. The decision will be made based on that specific area or specific region. So the workflow is that once the data set is being gathered, which is one of the most essential things, data cleaning is very essential because it determines the model results. Data cleaning and preprocessing, this include removal of missing numbers, duplicate columns, outlier detections, and the rest. Having done this, we look at feature engineering or data processing, which will look at the exploratory data analysis, correlation analysis. This is just to show the relationship between variables. And then we'll begin to look at which of these variables are we going to use as our predictor. And this will depend on our objective. Then we go to model building. Building the model is essential because it's the key part of the machine learning algorithm. We have several models ranging from the regression model. It can be simple linear regression. It can be multiple regression. It can also be classification model. For instance, random forest is generally common. We also have gradient boosting. We have decision tools and the rest. So after building the model, we also tune the hyperparameter to prevent overfitting and to enable efficient or performance. And this, having built the model, we need to look at the metrics. And looking at the metrics, there is metrics for the regression model and the metrics for classification model. The one with the highest metric or highest accuracy will be chosen to be used for the prediction or to be selected. So having trained the model, cross-validate and detune the hyperparameter to avoid overfitting. And then we also look at spatial analysis to look at the results on the spatial base. This will require maybe administrative boundary or elevation data, whichever one you may have at your disposal. And you ensure that you align the CRS together with your coordinates. And in running spatial analysis, this is a crucial aspect because one needs a valid coordinate in order to run the spatial analysis. And in running a spatial analysis, you may decide to opt for the simple, which is the inverse distance weight, or the kriging to account for spatial autocorrelation. This is to help us detect area that are actually, maybe for instance, we look at limitations, areas with high limitations, areas with low limitations, and the likes. So a case study is being shown here. A case study here is the use of machine learning model to estimate nutrient limitations and site-specific recommendations. This is a research still under study and being carried out to see areas with limitations of nitrogen, phosphorus, and potassium. These are key macronutrients that are actually very important in the soil. So the goal is to see where we actually require more of these nutrients and areas that do not actually require these nutrients. And for us to be able to know the type of fertilizers we apply in such kind of area. Not just that, we also look at the factors that actually influence limitations in those study area so that we will know how to correct the deficiencies. So the first thing that was done is the classification model to see those that belong to limitation classes and those that do not belong. So classification was done using the binary encoding. It was encoded, having encoded, then the matrix was used. And in that, we are using 3 predictors: nitrogen, phosphorus, and potassium. A multi-output ensemble model was actually used. Random forest, decision tree, gradient boosting, and stacking. So when this was done, the accuracy the metrics were actually itemized, and random forest, multi-output random forest happens to be the one with the highest accuracy, and it was chosen. So having done this, we also look at the regression model, which include all other variables, which also include the nutrient recommendation strategies. Look at the management, the weather factors, and the rest of the variables. And then they were mapped out. So the tools used was the Python, a Jupyter Note, one of a Jupyter Notebook, which was one of the powerful Python library, and the library used mostly here is scikit-learn. It's also very essential that you load other libraries for visualization, and then R can also be used, R Studio, for running this model. One good thing about it is that having a unified analysis, unification of machine learning with geostatistics workflow will help us, in a way of bringing together fragmented soil test data or data sets into a targeted, more understandable, spatially explicit data that can help inform decision or decision making. So once this data set is being gathered, just like I said earlier, we run exploratory data analysis to see the relationship between each of these variables, or the relationship between these predictors that will be used to run the model and other independent variables. Just like I said, this research that is going on is the use of nitrogen, phosphorus, and potassium as a predictor. So looking at this predictor, the relationship with other independent variables. So this is just an example of some of the visuals for the correlation matrix. And so having run the model, when the model is being run, there are some other features that is essential to look out for, part of which include the feature importance plots. This is an example of the feature importance plot. There is also partial dependence plots. There is also the sharp value. All these are very essential to see which of the factors or which of these independent variables actually influence these predictors. So look at this feature importance plots. We observe that the one with the highest importance is from the top downward. So look at it, it is mostly influenced by nutrient ratio, followed by the temperature and downward. So now, if we want to correct our limitations in those study area, we first of all look at how we can balance the nutrients. And this is just an example of the environment which is being run in the Jupyter Notebook and the Python, and this is for the R Studio. And this is just how the metrics look like for the regression model. So this is just an example. Look at the gradient boosting, the stacking, the multi-output random forest regressor. Look at the RMSE, the R square, which is very important. The one with the highest R square will be chosen as being the one with the highest accuracy. So we also look at the feature importance plot for it. So, and then that aside, we can also look at yield as a predictor. That is the factors that actually influence yield. And looking at the feature importance, we observe that it's mostly influenced by temperature, rainfall, and downward. So which means that in this study area, we actually worked with the yield of maize is mostly influenced by the climate or the weather variables, as the case may be. And another thing is that we don't just choose nutrient recommendation strategies. Instead, we adopt a metrics that can be used to see which of the nutrient recommendation strategy actually improve yield, and then efficient use of nutrients. So when this was done, it was observed that regional has more, is better than other recommendation strategy. Then the model, and then we decide to look at how we can compare this by transmitting the results. And the results of the model can actually be put into a user-friendly interface for others to input their data and see how efficient the model is working. So, and for the spatial analysis, administrative boundary was used, and then we are able to detect or to analyze areas with site-specific model recommendations. This is just an example, and this is an example of the spatial interpolation techniques using inverse distance weights. And for each of the study area, we can also be able to predict the nutrient use efficiency, yield, fertilizer use efficiency of each of one of them. So adopting this technology is very, very essential or very important, and then will be impactful, just like the professor has said. Smart agriculture is good, and this will help to, improve agricultural productivity. Not just that, and some other challenges that we face in the field of agriculture. So, calibrating this recommendation with local agronomic threshold is very important, and it also enable us to, when we want to validate, to make it more realistic. And one good thing is that developing this technology is one thing, and another thing is farmers, especially the small older farmers, to to reduce the stress and then in terms of the cost implication, this will help instead of blanket application of fertilizer that results in environmental footprints and then high costs associated with it, and also helps to improve the yield. So ground truthing is very essential. Ground truthing the result of the model is essential to know how well the model is working, and also scale this model or this technology to higher level, so it can be adopted by other users and for other crops. So for in terms of policy and future impact, policymakers can actually integrate this model into fertilizer subsidy programs, which will enable site-specific allocation of resources. That is, they will be able to know areas that actually need priority intervention. And this technology will also align with climate-smart agriculture by helping to promote input efficiency, reduce waste, and support sustainable intensification. And collaboration with other agricultural institutes is also essential so as to help scale up this technology. Thank you.
Thank you, Dr. Maryam, for your presentation. It's really nice work, and for showing us how machine learning is being used in predicting crop yield and also for nutrient recommendation. We now have floor for questions and comment for our last presenter. Please, you have the floor up, dear participants. You can open your microphone and ask any question you have. Thank you, Dr. Comey. Yes, our speakers have really done a great work, and they've shared with us some of the interesting research that they are doing in their respective organizations. There is a comment in the chat. SODCB is asking, can you organize training based on machine learning? Yes, I think last month we had a training from the modeling and mapping sub-community on digital soil mapping, and it was presented by Dr. Betony. So we do have frequent trainings, SODCB. Dr. Kome, please, you can open your microphone and ask your question. Thank you.
Thank you very much, dear Eric. I hope you can hear me.
Yes, we can hear you very clearly.
I will first begin by thanking all the presenters. The last question that was asked is in line with what I want to say. I don't have a particular question, but a comment.
Okay.
After following all the presenters, from the very first presenter to the last, I think that what they have showcased is far beyond a showcase and warrants some training, because I must say that what they had as content is so rich and very important that I think should not be limited to this showcase. It will be good that I'm happy to know that there is someone who already opted to share some techniques. So my humble suggestion would be to see how we can obtain more from these presenters, because the topics shared are very useful. We see very practical implications. And we hope that in the future arrangements could be made so that they give us a bit of their time again, so that some of us who are getting some of the techniques can benefit really and see how we apply this knowledge practically. That's what I had. Once again, I really want to thank all the presenters. Thank you.
Thank you, Dr. Kome, for your comment. I think it's in the right direction. And this platform or this showcase also let us know what our dear scientists are working on. And we can also link up with them and collaborate more in some of these areas of research. So please, let's feel free to contact Betony, Diana, if we want to know more about the Seedling process workflow for digital soil mapping, Musefa, Professor Abdel-Aziz, Dr. Maryam, and all our distinguished scientists here. I know we are doing great work in our respective countries and institutions. And yes, Soil Information Community of Practice would also continue from time to time come up with some of these trainings to also enlighten all of us in what we are doing in our respective research areas. So thank you, Dr. Kome. I know Crow have taken note of it and will be reaching out to us and inviting us to present and share with all of us within the community. Once again, we want to thank all our speakers for making time to share your research work with us. We really appreciate the efforts in preparing and also in delivering these presentations.